Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosine River College in Sacramento, California. This video is a continuation of the double angle identities in trigonometry. You should have already watched my videos on the double angle identities, the theorem and the proof, and then using the double angle identities. This specific video is on proving trigonometric identities. It says part 4 because I dedicate a part for every time we introduce a brand new style of identity. So this part 4 is dedicated to when you're introduced to double angle identities. You can now do proofs, more proofs that is, involving double angles. So let's go ahead and tackle this one right here. Let's prove that twice the cosecant of 2x is equal to tangent of x plus cotangent of x. Again, the tactic is usually to start with the most complicated side. Well, if you look at the most complicated side in this case, I would probably honestly start with the right-hand side. Even though I easily see there is an identity here, you might not think that's an identity, but that's actually 2 over the sine of the double angle, and we have an identity for the sine of the double angle. But I'm going to hold off on that for the moment because this is a great one to showcase strategy. So I'll start with the right-hand side. I'll just do that in green. Right-hand side. Actually, I'm going to use blue for the right-hand side. Right-hand side is equal to, again, tangent plus cotangent. So I'll just write that down. Tangent of x plus the cotangent of x. Now I'm going to take a look at where I want to arrive. I want to arrive at twice the cosecant. Well, I know cosecant involves sines, right? It's 2 over the sine of 2x. So I'm going to trade out this tangent, these tangents and cotangents for sines and cosines. Just a good idea. So I'll write this as a sine of x over a cosine of x plus cosine of x over sine of x. Again, I take a look at where I want to go. Well, I want to arrive at the left-hand side, which is a single term. It's just a single 2 times cosecant. So I need to glue these two things together into a single term. That means find the LCD, which is sine times cosine. So I'm going to multiply this first fraction by the sine, both numerator and denominator. So I'll get a sine squared of x over sine of x times cosine of x. And the next term, I'll multiply numerator and denominator by the cosine. So I'll get a cosine squared of x over sine of x times cosine of x. Now that they have the same denominator, I can just add them up. Remember, fractions, when you add them, you only add numerators. So this is sine squared of x plus cosine squared of x all over the sine of x times the cosine of x. And we know the Pythagorean identity that sine squared plus cosine squared is 1. So that's 1 over the sine of x times the cosine of x. Again, I take a look at where I want to arrive, and that doesn't look anything like the left-hand side. So I might pause there. Let me write pause. It's funny that I do this. I have a habit of just writing pause, just to tell myself I'm going to press pause here and work on the other side for a little bit. And it's funny, I've done that for years, and ever since I've been doing that, my students do that. So I see my students write pause on their exams, and I think, man, it's interesting how people really do listen. And even when it's just little silly things that I do that's not really mathematical, but that's fine. Write pause there if you want to. I've had other instructors say, are you the one that writes pause? Because all my students now write pause. Anyway, left-hand side. We're going to work on that for a little bit because Again, I paused on the right hand side. I don't know what to do with that. But if I move over to the left hand side, notice that's 2 times the cosecant of 2x. And I know that I can write the cosecant as 1 over the sine. So it's 1 over the sine of 2x. And now I know I have a double angle identity. Remember, the sine of 2x is 2 sine of x times the cosine of x. So this is going to be 2 over 2 times the sine of x times the cosine of x. Notice the 2's cancel beautifully, and this is 1 over the sine of x times the cosine of x. And if you look at where we paused, they are the same. So there are a couple ways you could say this. I would probably do it this way. I'd say equals right-hand side, because I've shown that the right-hand side is equal to 1 over the sine of x times the cosine of x. So left-hand side turned into 1 over the sine of left-hand side. Sorry, I'm pointing with my finger, so I have to do this. Left-hand side turns into 1 over sine of x times cosine of x. So therefore, left-hand side equals right-hand side. We are done. That is the proof. QED. Notice that's a really good way to do that proof. Work on one side for a little bit. I usually choose the most complicated side. Try to get it to at least get to one term rather than the sum of two things, because that's what the left-hand side is. It's one term. Once I get there, if I can't magically get it to look like the right-hand side, or the left-hand side, then I will just I'll pause, I'll jump over the left-hand side and work on that for a little bit and see if I can make them match eventually. Really good way of doing that proof. Now here is a problem that is a problem. I mean, it is a problem. It is a lot of work. It is very popular in calculus, specifically Calc 2, that you run into this style of problem. In Calc 2, you actually start working with stuff like this. And you need to expand that out. And the only way that you can expand that out is through powers. So if you look at this identity that they're asking us to prove, which is not a memorizable identity, okay? None of these that you're proving within examples, none of these are memorizable. These are generally ones you don't want to commit to memory, but because there are hundreds of trig identities, if not thousands, honestly. And you could not possibly commit all those to memory. So the ones you want to commit to memory are like the Pythagorean identities and the sum and difference of angles identities, the reciprocal identities, the ratio identities, the double angle identities. Those are all important ones. But these ones that we're doing in examples, do not just memorize these. That'd be silly. Unless you have a photographic memory, good for you. Now, if I'm going to prove this, and if I have never had trigonometry before, I have heard my instructor say repeatedly, tackle the most complicated side first. I'm going to tell you that is actually a bad idea in this case. It's very, very hard to start with powers of trig functions that are not just squares. So you see you have a cosine to the fourth and a sine to the fourth there. It's very hard to start with stuff like that and compress it down to just a cosine of a multiple angle. Instead, I'm going to work with my trig identity. I have this cosine of a multiple angle. And you may say, but I don't have a trig identity for the cosine of fourth theta. You do. You really truthfully do. I'm going to write it off to the right-hand side. Let's just write it off to the right. You have a trig identity that says the cosine of 2a, I'll write it that way, is equal to the cosine squared of a minus the sine squared of a. That was from our double angle identities 2 videos ago. Or you could rewrite that in 2 other forms. It could be 2 cosine squared of a minus 1, or 1 minus 2 sine squared of a. Now, you could see the right-hand side of this identity that they're having us prove has a mixture of sines and cosines. So I'm going to use the first version here. And you still say, but that's not a cosine of 4 theta. I know it's not. But we're going to let a here equal 2 theta. If you let a equal 2 theta, then you're looking at the cosine of 2 times 2 theta, or in other words, cosine of 4 theta. Let me go ahead and write it this way. If I work on the left-hand side, it's cosine of 4 theta. But cosine of 4 theta is the same thing as the cosine of twice 2 theta. Well, twice 2 theta, I'm going to write that in a different color for now. I'm going to write that 2 theta in a different color. So therefore, that's the cosine of a double blue angle. Okay. And we know that the cosine of double angle is going to be the cosine squared of that blue angle. Green. Minus sine squared of that same blue angle. So I am actually using a double angle formula here. Now, this does not look like, at least to me, the right-hand side as of yet. However, those are now that's a cosine squared of a double angle, and that's sine squared of a double angle. So let's go ahead and trade out that cosine squared of a double angle, and I'm going to make it look like this first. I'm going to say that's the cosine of that 2 theta being squared minus a sine of that 2 theta being squared. It just makes it a little bit easier for you and me to see the same thing. Cosine squared of 2 theta is the same thing as the quantity of cosine of 2 theta being squared. These two things are exactly the same statement. But we know that the cosine of the double angle can be swapped out for the cosine squared of the regular angle minus sine squared, again, of the regular angle. And remember, we're squaring that. So all I did was trade out this picture for this stuff. But remember, the square is still hanging out on the outside. Okay. All right. And I'll do the same thing for the sine. The sine of the double angle is twice the sine of the regular angle times the cosine of the regular angle. And again, that's being squared as well. It still does not look like the right-hand side, but it's getting close. Now we're going to go ahead and square this out. Cosine squared minus sine squared being squared. Well, that's like an a squared minus b squared being squared. That'd be a to the fourth minus 2a squared b squared plus b to the fourth. So I'm going to go ahead and do that. It'll be cosine to the fourth. I don't go through slowly on this because algebra is generally a prerequisite for all of trigonometry. So you should have gone through algebra and a little bit of college algebra before taking a trigonometry course. So this should be like easy breezy stuff. So you should be okay with this. Cosine squared theta, sine squared theta, and then plus sine to the fourth of theta. And then we also have this minus right here, and then we're going to square 2 sine theta cosine theta, and that'll be a 4 sine squared theta cosine squared theta. And we're getting very close to the identity that we're trying to prove. We just have to combine like terms. Notice that this picture right here is the same as this picture. They're kind of not written in the right order, but they're the same picture. Remember, multiplication is commutative, so you can actually rewrite that second group, sine squared, negative 4 sine squared cosine squared, as negative 4 cosine squared sine squared. So this will equal cosine to the fourth power of theta minus 6 cosine squared of theta sine squared of theta plus sine to the fourth of theta. Now let's see if they look the same, and they do. They look identical. So this is equal to the right-hand side, and we are done. Check. So that's a really, really good proof. That's actually a really good level of proof for exams and stuff like that. The hardest part, I think, for students is to recognize how to start this problem. If generally speaking, with trig proofs, you start on the most complicated side. Obviously, the right-hand side looks like the most complicated side, but it is also really hard to work with. So often, if you see a trig identity right from the get-go, you might as well just start with that trig identity. In fact, in the previous problem, we could have started, we started on the right-hand side in the previous problem, but we could have started on the left-hand side. That's actually what I normally would do. I'd just say, oh, there's a trig identity right there. Let me go ahead and rewrite the left-hand side in terms of that trig identity, which is sine of 2x. And I would have gotten down to this part right here. And then I would say, oh, well, that's not exactly tangent plus cotangent. So let me move over to the right-hand side and work on that. And that's how I probably would have done this problem as well. It's just start with the trig identity. And then if I get stuck, switch to the other side. So that rule of thumb of starting on the most complicated side is just that, a rule of thumb. You will break that rule all the time, mainly because you'll see a trig identity and you want to take care of trig identities really, if you can, first. All right, that's it for this video. There's no other proofs in this video. We'll see some more in a future video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.